Same bed.
Yeah, but what
That's centrifugal force going on?
like, you know, turning cup makes video game
Yes, I'm down for it. Yeah. Yeah, we down. Are you guys down? Yes, yes, yes. Okay, then I gotta get it. After the quiz, just forget about everything, you know? Next time the quiz. Okay, I work here. I don't like yeah. I could use my bike so you know, try that. Look at that thing every else is kind of data. So basically, I don't know. Yeah, it comes out converting one language to another. You want it to me? Yeah. You can. You're different. You're right. Who cares about money for the discovery? You can make gold out of I can make mass-produced cars.
It looks like I'm looks like I'm turning this around, right? It's kind of doing its own thing.
Not at all. Maybe it's a whole lot of that.
Anybody can do this. And if I grab it on the other side, oh, it goes the other way. Is there any skeptics here? Does anyone think I'm doing this?
I think so.
Come on up.
I'm kidding.
I want you to prove it to yourself. I'm not going to do that. It's his. I'm responsible for it. I can actually, if I know what I'm doing, see, I'm going to push back and forth, and what's going to happen?
Resist.
Now, this is kind of physics, but it does have something to do with what we're doing. Yeah, I'm just going to.
Yeah, I think so. Don't worry about it.
I'll just put it over here for now.
We should try that right there on my.
Yeah. There's actually there's a great one I saw, a video. This guy's got like a barbell with one thing on it.
Oh, I saw that.
Yeah, and one guy, you know, they say, well, you're, you know, strong man, you know, pick it up, and he can't. But then they spin the bar, and this guy just picks it right up. I have a lot of things to talk about, but I want to give you the kind of distinct perspective here. So, anybody who worked on the homework and has questions, we're going to have some minutes to talk about that. And if nobody worked on them, well, we're going to kind of work on them anyway. There's a quiz on Tuesday on vectors. We pretty much covered everything that's going to be on it. You know, and of course, we'll do a little review of what kind of stuff. But I have so many things I want to talk about. But I want to talk about like bad books. Bad books. This book is not. It's not only as bad, but it's spotty. It kind of leaves a lot of the really neat things about vectors out. And I'm just going to talk a little bit about them so you can see them before they run you over in your physics class. Ken, did you get your stuff from here? Did you need yours?
He fixed some things.
I'm going to pick a fight here with the book here, just briefly. Oh, it's just going on all by itself. So, Determine whether the given quantity is a vector or a scalar. So, it says the force needed to lift a box. Is that a vector or a scalar? Yeah. So vector's the answer they want you to give, and it's perfectly okay. But yeah, I think it's ambiguous because if you're lifting something, there's no, I mean, there's a direction to it, but there's only one lifting direction, right? You can't lift it this way or this way. I'm being kind of anal about it, I guess. It's a bad question. They shouldn't give an ambiguous question. The same thing, tension in a suspension bridge cable. Well, yeah. If they just said force on a suspension bridge cable, I'd say, well, that's definitely a vector. The tension in a cable is along the cable. So there's no question about the direction. There's just what its magnitude is, which is scalar. Okay, we'll go over some of these. This thing, I guess YouTube does this. You're looking at something and it goes back and, oh, now we have to skip the ad.
Some of that. You can ad block, it's free, and it'll get rid of the whole ads, including video.
So we're also going to do some problems related to vectors, but we'll get to that. This will be more fun for a minute. Okay, so anybody ever own one of these? This is a toy, right? Yeah. They're not as common as they used to be because toys are so much more sophisticated, you know, iPads, whatever. But this is just a cute little toy, and it demonstrates kind of what we were looking at with the wheel. I'll just let this run. And it has something to do with vectors, which I can't really make part of the class because it doesn't show up in 2 dimensions. There's actually something cool about space-time that this has to do with. When we're just dealing with vectors in 2 dimensions, you know, the world is not 2-dimensional, right? But a lot of times, like if you're driving on a road, you can kind of ignore the fact there are hills and it's just 2-dimensional. And problems are much easier in 2 dimensions, and vectors are much easier. You know, one of the things to think of is symmetry. And if you look in 2 dimensions, symmetry is pretty simple. Like you have a vector going this way, you know, another vector can go that way. Or, I guess to make it even simpler, we have an axis that goes off in one direction, it goes off in the other, it goes up, it goes down. So they're really 2 directions of symmetry. If you add a 3rd dimension, you know, X, Y, and Z, well, of course you get that other symmetry there. But something shows up that's kind of neat. Are there any biology students here? Okay, good. So have you gotten to where you know what dextro and nilo is?
Some type of dog, right?
Dex. Dex. Nilo. I think I spelled that. They're probably Latin or something. Left and right. Yeah. Well, you've heard of it. Okay. Like dextrose is a sugar. Right. So what happens in 3 dimensions with molecules is you get a molecule, and there's one molecule, you know, there's one. Oh, let's turn that off. I like it. I'll go turn it off. There's no off. It's just What was I saying? Something about dextro. They're molecules that they're attached exactly the same way, but in 3 dimensions, they're 2 different variants of it. Now, here's a really good way to think of it. I have a hand, right? I have another hand. They're different. How are they different? There's the dextro and the levo hand, right? There's something that happens in 3 dimensions that, you know, this hand is different from this hand.
Ambidextrous?
Yes, but when you reflect them, they're different, right? I mean, in a different way.
This is a very broad question. This is a very broad question.
It is, yeah. I'm not, you know, they have different fingerprints too. I don't mean that, but yeah, it has something to do with the. Okay, so let me just show you kind of what the deal is. If you have 2 vectors in 3 dimensions, have 2 vectors in 3 dimensions, there's an operation on them which is a multiplication, and it's called a cross product. And if you're into physics, you're definitely gonna find out about this. And so we have like vector v and cross product vector u, and the result is another vector, only it's kind of perpendicular to these vectors. It sticks out of the board. And, I guess we'll use this again.
Is there like another axis?
Well, we're in 3 dimensions, so we got, right? These are in a plane, right? And the cross product is perpendicular. So
the reason we haven't been multiplying vectors is because when you do, you get a third dimension.
we're going to multiply vectors a little later,
But
and we're not going to need a 3rd dimension. But I'm just, I just want you to see where this comes in.
What is the x sign? Or is that
v times u.
Is that like a multiplication sign? What is
V
that
times u equals w.
It's like an x. It's called a cross product. Okay, so let's look at this guy for a second. So when this is spinning, does anyone know what we call the momentum of a spinning object?
Centrifugal force?
It's an angular momentum, right? Angular momentum. So there's 2 angular momentums going on here. One of them is the spinning wheel. And it turns out the vector for the spinning wheel goes out this way or this way, depending upon which way the wheel is spinning. But there's another, now if I'm just holding it like this, it's just going to spin like this. But if I let go, what happens is, or I'll just stop it, gravity is pulling down. So there's another angular momentum, well, it's not angular momentum, it's an angular force pulling it down, right? And you take these 2 vectors, the one going this way and the one going this way. All right, maybe I should draw a little diagram. So we have the wheel, and there's a vector going this way, and there's a force going this way, and we take this cross product of them, it's going perpendicular. So take a look, vector this way, and what happens? Oops. The motion is now in this direction. Now, of course, it's going in a circle because every time it moves it a little, that direction changes. But anyway, this is just something really cool about vectors that I'm not allowed to teach you because it's too advanced. Okay, so that was, I wanted to say that. And there's another really cool thing here, which is when you look at this symmetry, you would think, well, if you think about the universe, like if you're going in this direction or you're going in that direction, it's the same thing, right? The universe is symmetric. If you're going in this direction, and this direction, and this direction, and this direction, these symmetries are assumed to be perfect. There's no difference. Turns out I think about 60 years ago, someone did a very peculiar experiment where they were measuring the symmetry of left-handedness and right-handedness, and they found out that the universe is not perfectly symmetric that way. It's slightly off. Kind of weird.
What do you mean?
Well, what the experiment was had to do with a certain kind of atom, which has an electron going around it, and it has a spin, right? And the spin is either left-handed or right-handed. And there's no reason that there should be more left-handed spins than right-handed spins. But there are. So now we shouldn't be totally shocked at this because in the case of molecules, in our proteins in particular, proteins can be left-handed or right-handed. In the human body, most of them are, I think it's left-handed. And actually, there are a lot of things where the left-handed version is perfectly fine for human consumption, and the right-handed version is poisonous. So there are other things that aren't symmetric. We also, how many lefties do we have in this class? And I don't mean political. How many left-handed people?
Well, it's California.
Yeah, I was just about to say that.
You see, there aren't very many left-handed people. So, that's just on the Earth. We don't really, that's not a big deal. There are plenty of,
I mean, you can't really even judge that as being natural or denatural anymore either because of Catholicism and like how you couldn't be left-handed. You would get beaten in Catholic school and stuff growing up.
Is it hereditary?
Yeah, but it doesn't usually work.
Yeah, my brother's left-handed.
When you beat someone to be right-handed who's left-handed,
It was shunned against.
it usually doesn't work, really.
Well, my father became ambidextrous. He was left-handed, but in the Soviet Union, they didn't want you to be left-handed, so they forced him to break with his right hand, so now he can write with both equally well.
It's kind of bizarre, isn't it? They wouldn't want you to be left-handed in the Soviet Union. But that's just
Why did they care?
ethnic joke of some kind, or political joke. Yeah, no, that's
The only
historically,
possible
they don't do that.
is maybe if there's
that
something
much.
about the gun weapon design that
I don't know if it's genetic, but
Most of their
I'm not left-handed. We had my father was left-handed, my brother's left-handed, so maybe, I don't know.
Yeah.
Okay, so let's I don't know what order to do things in. So let me just ask, did anybody work on the homework and have questions about it? Yes.
Well, I guess this isn't the homework, but are we going to learn how to do number 6 on the
homework?
On the white sheet.
Oh, on the white sheet. Oh. Okay. Perfectly valid.
So do we do it?
Question. Oh, yeah. I still have some. If anybody didn't get one, I have some. It's also on the web. Even if you took one and you want another one, you can take it. This is just problems we're doing in class. I'm down to my... Okay, so you want to know about 6. Chris, you want to know about 6?
Yeah.
Yeah. Okay. It looks kind of like another problem we did, didn't it? Doesn't it? Yeah. This one's easier. Well, it's not really. It's the same thing, but the numbers are easier. All right, let's take a look at this again. So it's easier because I can mostly do it without a calculator. So we've got a balloon and it's pushing upwards at 100 pounds. That is to say, to keep it from going up, you would need to pull down, you need like a 100-pound weight. And again, you want to know why is a 100-pound weight a 100-pound weight? Because that's the force of gravity pulling it down. But we don't hold it down this way. I'm going to leave this line here because it's convenient. But we have some guy ropes here. This one's at 60 degrees and this one's at 45. And it's not moving back and forth, which means that the horizontal forces on it are equal. So this force and this force. The real forces actually, I guess, are. I'm gonna try and make it less confusing than on Tuesday. I'm just gonna call these X and Y because I think it'll be simpler. Instead of F1 and F2, and then I have all these other indexes. So I have some. I use my geometry, and I have some triangles here, and now I can figure out what this angle is. Do you want to tell me what that angle is?
60.
Yeah.
60.
Does anyone want to go so far as to tell me what geometry property tells me that that's 60?
Oh,
Very good. How many years ago did you learn that?
it's been a while.
Okay.
5.
These are parallel lines. This is a transversal. These are opposite interior angles. And they're equal. Okay. So that's 60 degrees. We've got a 30, 60, 90 triangle here. So this, if this is x, what must this force be? One. Both of these would be really important. 1. What's this side?
No. 1/2. That's
1/2, right? You draw the whole 60, 60, 60, 60 triangle.
3 over 2.
Right?
The last side's 3 over 2.
Square root of 3 over 2. Good. Okay. So this is x, and this has to be 1/2 x. Okay. But while we're at it, let's draw in 1/2 x. This one's square root of 3 over 2x. Now this guy, he's a 45. You should know this without me even hinting. These are all 45-degree angles. So this is y. What is this?
Y over root 2.
I'm sorry?
Y over root 2.
Yeah, or 1 over, I'm going to write it this way, run over root 2y. And why are these, well, why are these equal?
Because the balloon is stationary, it's not moving left or right.
So they have to compensate. Remember, the rule is with forces, if it's not moving, they have to add up to 0. And that's component-wise, the x direction and the y direction. Yes? Oh, sorry. Okay, so now that's one equation. Where are we going to get the other equation from? Well, this is a force pulling this down. This is a force pulling it down. Oh, this is also 1 over square root of 2y. And we add those up, and what do we get?
Add what up?
the force of this wire in this direction and the force of this wire in this direction. What do those have to add up to?
100?
100, right? Because there's force going up this way and it's not moving. So square root of 3 over 2x plus 1 over square root of 2y equals 100. Okay. So you have some choice here. You could, I guess, you probably never had a problem like this in Algebra 1 with roots, right? But it's no different. I mean, they're just coefficients on the x and the y. So we can use either of our methods here. I think yesterday we used substitution, but some problems substitution's easier, some elimination's easier. This one, you can go either way. What I'm going to do is I'm going to subtract the two sides of this equation. I guess I want to write it this way so it's a little clearer. I'm going to subtract the two sides of this equation from the two sides of this equation. Anyone see why I want to do that? And get rid of the y, yeah. This turns out to be pretty easy. All right, so this equation minus this. On this side, I have square root of 3 over 2x. 1 over square root of 2y minus 1 over square root of 2y, of course, is 0. And I just have 100 minus 1/2 x. Okay, I'm going to rewrite this so it's really clear. Square root of 3 over 2x plus 1 over the square root of 2y equals 100. That's the first equation. The second equation is 1 over the square root of 2y equals 1/2 x. So think this is a big subtraction problem. Are we good? The top equation, there's the bottom, I'm just going to subtract. Here I get square root of 3 over 2x. Here I get 0. Here I get 100 minus 1/2 x. You okay with this?
Why did we subtract like that?
Because it will eliminate the y.
Is that the same as solving y in terms of x?
It's not the same as substitution. If I was going to substitute, what I'd do is I'd probably multiply both sides of this equation by 2. And then I just have x equals, and I can substitute x equals back.
How is this way? What's different about this way? Why can you do it this way?
Well, this is called elimination, and basically you take one or both of the equations. If you have to, you multiply them by a constant, and then you add them or subtract them in a way that eliminates one of the variables.
Why did we move 1/2 over x to the left side?
Why didn't I move this over here?
Yeah.
You mean like,
Wouldn't that have made it easier?
I could, and then I'm subtracting a negative, and it'll become a positive over there, but I'm gonna get it over there anyway.
Okay.
I mean, yeah, you could do that. All right, so this isn't here anymore. I'm going to add 1/2 x to both sides. I get square root of 3 over 2 plus 1/2 times x equals 100. And then I just divide by the square root of 3 over 2 plus 1/2, which I'm going to write that over here. X equals 100 over, and then this was really square root of 3 plus 1 over 2, right? So I'm going to divide by that, square root of 3 plus 1 over 2. And that becomes 200 over the square root of 3 plus 1. So that's my x. Now,
Looking for X and off the Y.
Joel.
So now we replace X with what you just solved before and solve the Y, right?
Yeah, I mean, we could find a decimal number and get an approximation, or we could just see if we just plug this in. Maybe that works nicely. That's an exact number, isn't that nice? Not that there are balloons with exact forces on them, but. All right, I think we can substitute that back into either of these, but I kind of think that it'd be easier to substitute it into this one. All right? So, draw a little box here. So I have 1 over the square root of 2 equals 1/2 x, which I'm just going to copy down. 200 over square root of 3 plus 1. And I'm just going to, I hope this doesn't hurt anybody's feelings, I'm just going to erase the half here and make that 1. Okay? Factor of 2. And now I can, oh, wait, I left out something. I left out the y. And now if I multiply by the square root of 2 on both sides, I'll just get y equals square root of 2 times 100 over the square root of 3 plus 1. All right, that's it. So now I have 2 exact answers. If I want, you know, scientific notation, I can put them in my calculator and figure out the decimal. Yes?
So where did the 1 over square root of 2y equals 1/2 x come from?
Okay. This vector and this vector are equal. This is a 30, 60, 90 triangle. So this up here is 1/2 x. That's where the 1/2 x came from. This is a 45, 45, 90 triangle. This is y, so this is y times 1 over the square root of 2. This vector. Its magnitude is y times 1 over the square root of 2. And so I'm just saying these two are equal. These two vectors are equal.
And we know those two are equal because it's not moving from side to side.
It's not moving from side to side.
Okay.
Okay. I think, any other questions about this, or the sheet, or the homework? Yeah?
Number 5 seems, I couldn't really
Yeah, it
tell
seems
what
too
was-
easy, doesn't it?
Yeah.
Yeah, it was.
Okay, that's what confused me.
It seemed like a trick question.
This is not an uncommon problem on tests. Something, no, we're going to use, you know, differentiable integral calculus to add A and B. You know, no, it's just really there's a kind of a pearl of wisdom in this. We got a river. We've got a boat, and the boat is traveling in this direction. Got a little putt-putt motor, and it's going to propel it at 3 miles an hour. See, if you forget the rest of the problem right now, and then you go straight to the question, it takes an hour to cross the river. How wide is the river? Then it's kind of simple, right? So this is 3 miles per hour. So let's see, V equals 3 miles per hour. Time equals 1 hour. And what's the equation we're looking for? What's the equation? Velocity times time equals distance. So all of a sudden it's painfully obvious that it's 3 miles across. All right, that's the first part. The river is moving along at 2 miles an hour, and like flying through the air, through the wind. The river is going this way at 2 miles per hour. After an hour, how far downstream do I end up? Well, it's the same equation, right? The little pearl of wisdom is that if you break a vector up into its components, like a velocity vector, you can kind of do something a little more simply. I mean, it would have been different if I would have said, tell me what's the velocity vector on, relative to land, right? Well, you'd say, well, it's going up at 3 miles per hour, and it's going to the right at 2 because of the water, so that's square root of 3 squared plus 2 squared. So that's square root of 13. And what's the angle here? Well, arctan or tangent inverse of 2 over 3, which is some weird number. I guess what this problem needs is a question. What's the distance covered?
It's like 3.6, which is the square root of 50.
Yeah. Okay, don't be thrown by a question that's too simple. And if it's too hard, think, maybe I'm reading it wrong and it's really simple.
I think I'm with that. I feel like if you're traveling at the diagonal 3 miles an hour,
I didn't.
it's actually.
Well, actually, yeah, you have to look at the problem. What does it actually say?
And that's how wide the river is. And if you're traveling at a diagonal at 2 miles an hour and you're traveling.
It's a bad problem. It's ambiguous, isn't it?
So, yeah, I'm reading it there. It's actually going to be.
Okay. So let's see if we can. Let's see what we can do with that.
But the
So it's going 3 miles an hour this direction, but it's being propelled 2 miles an hour by the river. So what's this component? How do I figure out that component? Let me draw that again. Here's its actual velocity vector, and we're changing the problem now, at least I think we are, but it's fair. So it's going 3 miles per hour this way, and we know the river is part of that, is propelling it at 2 miles per hour. So how would I find out its actual kind of speed across the river if the river weren't moving? Yes?
You take the magnitude of that hypotenuse basically,
That's 3, yeah.
then you use the slope to find the other angle.
It's much easier.
It's Pythagorean theorem, right?
Pythagorean theorem, right?
Angle, but
Yeah. So this is the square root of 9 minus 4, or square root of 5.
Okay, so that would be the distance across.
No, this is the velocity,
Okay.
right? So again, we go back here. Oh, you're right. The number is the same distance. Square root of 5 miles per hour times. It's going to be square root of 5 miles. Yes. Yeah. That's. If I ever give you a problem like that, and it's ambiguous, and I interpret it one way, and I mark it wrong, and you say, wait, that's ambiguous, I will. You don't have to guess what I'm thinking. That's a harder problem, too. It's got square rooted. Scary. Okay. I think this is a good time. I'm going to pass out some problems. We'll start with the first 2 and first 3. And these are very hard problems. So, you know, definitely if you're like scratching your head and you're not working together, you can work with other people. But, I mean, they're not like PhD thesis kind of problems, but. Passive moving back. Are there going to be extras? Oh, you have it already. Yeah. Let's just say, let's just do 1 and 2. And then we'll take a look at the results.
That's my thing, sir. Oh, I'm sure. So I'm ready. Yeah, flight and airspeeds. You said fear. Sorry.
So just to be clear, since this question came up on the river problem, number 1, an airplane flies at an airspeed through the air of 425 miles per hour. Now, it's not including any speed that the air imparts on it. That would be, when you do include that, that's what they call the ground speed.
You really can't unfortunately figure that out. Yeah. Here. The issue may never be correct. Leave back the insomnia disorder.
Yes, it's actually close. Wow. Yeah, it's pretty cool. Yeah, like.
If you don't matter. No, exactly. They hear it, they're
can't put my hair in dropping.
Possibly the sun actually takes us by. Unfortunately, I got like a friend who's the spreadsheet maker will know where every single
Maybe get in the fight with the bear, shear your hair off.
Let's get over to the question.
It's so depressing.
Pop the question. What's the question? You get the joke? Oh.
Well, you could interpret it that way, in the sense that it tells you wherever it's heading south, and the wind is 30 degrees east of the south. Yes. Okay.
So the wind's going this way.
No, it's going 10 miles per hour. At a 30 degree.
Let's pop the big question.
I missed the key word.
It's 100% at a 30 degree angle, right? Yeah, I got that.
Yeah, I think I can figure out what you got it.
You got it right, You're good.
I figured out that these are both ends, so this means this is 90 degrees, this is 160, so you can figure out the angle right here and do it law of cosine.
That's what I was thinking. I realized she has kind of been soft recently. Used to be like kind of like structural, mild.
Is everyone done with number 1 yet?
No.
No, oh, okay, yeah, these are hard problems, okay, go ahead.
We'll let you know.
All right.
We need to separate so it's north and west.
defined as ground speed. So its ground speed is the sum of those vectors. And its components in the westerly and southerly directions. So you have to. Wherever the answer, you know, I think
you want to know how to set it a bullet.
maybe, I don't know, or try to.
The camera presses the other day.
Alright, I'll still work with that.
X-ray feed through so
It's like high school.
The bullet that was launched,
Results here.
launched into the person and it wouldn't show. Yeah, you have a
I've run into this elsewhere. It seems, and I don't understand it. Maybe it's self-interest. Like, why would you be a teacher and want to make,
check the
I mean, you want to make your life as easy as possible within the bounds of what you're supposed to be doing. But one way to make your life easier would be to, you know, terrorize students so they hate you and then have as few as possible.
No, I think you just realize how it is. You can
Okay, it's sincere.
Because they want to
Well, that's one way to do it. So let me just show you this. So this is going south, and the wind is going 30 degrees east, that's that direction of south. So south would be this direction, and then 30 degrees that direction. So I think the arrow goes in like one.
That's why again, it's like minusing a headwind just moves on the opposite direction of the plane. Or else it would be tailwind.
Damn, another ambiguous problem. I think, you know, I have to, any aviators here?
Yeah, definitely.
You'll have to ask him. I think that a headwind is any wind that is not tailwind. Tailwind being, but you might be right. I mean, you're gonna Google it?
Yeah.
Okay.
A headwind is always.
It's flying against, it says flying against the headwind, so it has to be going in the opposite direction of the plane.
It says plane's going south, and the quote headwind is 30 degrees
Yeah,
east.
the wind is going that way, the plane is going this way.
The headwind is not going 30 degrees.
That's
It's 30 degrees coming.
sorry?
A headwind is wind blowing from directly in front of opposing the forward motion.
That's what I thought.
Yeah.
This is way easier. It's only
I hear your point.
Okay. It says headwind.
It does say it's a headwind. However, it also says 30 degrees east
Well, then the
of
word is wrong.
south.
No.
Well, like about number 2, they threw it out, so it's very clear, like, this is what we want.
And then it would be headwind.
Yeah, that was our last teacher.
Could it be saying 30 degrees east?
48C,
All of the sound?
Yeah, so, and that's why everyone's getting confused right now, because they don't know which numbers apply to the ones that.
The last professor at this boot camp, like, I took one of these in, I had no pages left in it. So that's why I don't stick around for half the class. Yeah, done with the book, go home.
That one.
So it's just coming straight.
Yeah. to make it fit the words, right? I'm okay to head in. It's 30 degrees east. Yeah, but then to be that way.
That's what we came up with too.
So now we have 3 interpretations. I'll tell you what, however you've been trying to solve it is okay. We'll look at it all 3 ways.
I think the actual I didn't say
Any difference in terms of just the way the diagram? If I draw the diagram, sure, okay, pushing this direction, but then the way I look at this, the numbers all going to come out the same, which makes no sense whatsoever.
Now, okay, that's
Goes through this one. You just draw a parallelogram and you sort of, triangles and then you use some geometry and be like, well, if it's 30 degrees, this direction, if I draw, just a vertical line, it's 30 degrees, and then I guess, 50. It ends up being
wait, now I'm thinking about it, it doesn't even matter how I draw it, because I'm just plugging numbers to get the same thing.
It makes no sense, because theoretically that plane should be...
I hope you're going forward.
What are you going to end up getting?
I think it's drop for the original.
They're trying to figure it out. Except this is for
Yeah, they'll figure out that.
Our diagram doesn't matter.
Because I was trying it from here, whereas in the previous just draw from there,
I'm going to say this loud in case anyone else is confused about this. When you want to add the component, the displacement component vector,
no, there's drawing wrong.
I'm not the only one. Although I was pushing the thing back. You're stuck. When you're adding components, vectors, the tail has to be at 0, 0, right? So in this interpretation of the problem, the planes vector is 0, negative 4, 2, 5. Because this point, this is the origin, this is 0, 0, and this is, the direction he's going, right? In other words, in this form, this is the head, and the tail is 0, 0. Everybody got that?
Correct.
Okay.
Wait, where is the plane?
apparently, this is the plane coming down. Apparently there are two interpretations of the wind, both of which we've decided are valid. See, the tricky part is it says it's a headwind, and that means it's got to be coming at it. Yes?
So on the quiz that were test, you wouldn't give us a problem with such ambiguous wording.
I would not. And if I did, however you decide to answer it, I would have to accept.
Okay.
However you choose to interpret the ambiguity. That's why I don't like this question. The force needed to lift it off. It's ambiguous. Yes?
You made saying it's coming from this direction, not going in this direction.
Yeah. Maybe at the same time you could say.
Well, in this interpretation, it's either this or this. However, my original reading was
How do you
it's
interpret
going in the other direction. So you can do it either way.
Okay, so that's what I was going to ask. Do you say like that, or do you?
That's just what I said. I mean, if you want, say what is that? Like 7 degrees south of west. Yeah, my
If you were north, could you just put the degree? You have to say like say this one is saying I got B this angle would be 21 degrees, so it's like do I say the direction is 111 degrees, or do I go 21 degrees?
I remember the ways to be done, and the only one I definitely remember was like south of east or north of west. But I think you could also probably
Forget what it says here.
is you assume north is 0. I don't know, you have to ask him, and I
Now to do that,
if you said, assuming that, if you like wrote out, like assuming that north is 0, it's varying, you know, if north is 0 and going west is the positive direction, it's varying, you know, I think you can.
okay,
Hello.
why don't we, you can keep working, but why don't we're going to take a break for about 5 minutes, and then we'll go over this problem. Apparently it's much harder than I thought it was. I think you lost me a little there. And how long is going now? Okay, so the components of this are the plane are yes, okay. And the components for the wind are
because I need to. Actually, my friend got me from the UK. Is that pretty cool? It's parcel.
It's the same.
It's a mailbox. Not a real big mailbox.
Depleted.
Twix and Snickers are best. I'm not concerned about my eating habits. Oh no. Oh my god, there was some girl selling cookies at the Girl Scout in the city. She was like next door, like our office, I believe. I think, whoa, girl, damn it. I was like, I got work on the side. Well, I'll come back later. What's that? Dude, because you don't go places where it's
That would mean the hypotenuse is smaller than a letter. Oh, 55 or 55 or 3. Maybe that's wild.
I think that's over about minus 25. It's like that.
That's the angle.
I know what it is.
I like that. Are you struggling? You look like you're struggling. Take a break. Take a break. Let your brain relax. Oh, yeah, I understand. There won't be too much. There won't be too much. Oh.
Team's closing. Remember when I talked about closing that the only idiots cannot see it?
Now, what I done wrong was I didn't have I done it with just 5 degrees. So I had to fix it. I fixed it because I had this. That's why I got it. So my ultimate answer was. Because my angel was
Especially with work problems.
Have you heard of the student become Mordecai?
Oh,
yeah.
I did it. I found it. I did it because I think that's what I did. This way it's more money or trade.
And then my dad discouraged me.
And that's why we learn it.
That African definitely bad.
Actually, I got those. I got those. Yeah.
In the East, but you know what? Top 5.
Right, this is,
Oh,
For the problem.
30, 60, 90, and then
yeah, but if it wasn't 30, it would have to be a sign.
I understand that, but since we know 30 and we knew one side, we knew the portions.
Got a question?
Pretty bad. Anyway, so
2 mile an hour, 3 mile an hour?
no, it's not just a bunch of special effects. I just got kind of an hour come over right now.
Zero. It's a lot. It's very sciencey. So zero.
I like your arrow.
Science fiction.
Why zero? Here.
Well, it's not the only line.
That's what I don't know. Look at the distance.
Well, it's heading, I
I
think.
can't show zero. What's that?
Although it's kind of moving up and down.
Right, so viewpoint,
Yeah, there's a lot of times it's 2 hours and then you have to figure out the degree.
here.
Yeah.
So
So
you gotta get in standard form, right?
Yes, that's right.
Sorry, you just missed it.
Now, remember, there are 2 ways to interpret
Yeah,
thesis,
that's how I started.
and then this was the well-written problem.
Oh, you gotta find out like how many knows.
Along the line, this vector was 3 miles. That's the other interpretation.
No, you're just.
Black hole.
But isn't that kind of interesting?
Arrow point, right?
A little bit.
At the same time.
This is more applied to.
Well, actually, it is pretty good.
What's part of it?
Well, that's
Right.
I feel like it's one thing.
Yeah, I know, we're gonna have to be. Have you heard of gravity? How was it?
They got a lot of the like.
I guess.
Science part, right? Right.
It's just,
You can't get away from it.
it was just when her link through space until she
The
died.
next section,
That's scary. That's all I
battery
got.
is gonna splash right
That's
into it.
the question.
Like some.
Yeah, the battery in theory is gonna go.
Thrown out into.
Yeah, I understand it to be. If this is 0, 0.
Essentially, the end of the number.
What's that?
Because you need that to hold it here.
I guess I can drop down to anything else.
Yeah, I wonder if you can stop that.
It's just 2 ways to interpret.
Okay, we should get going again,
Small.
even though everyone isn't here. Does anybody outside smoking that needs to come in? David, would you just let them know we're starting in case they want to come in? Thank you. What happens when you sit by the door? Thank you. There's nobody there. You're gone.
We can do County Central, then but I thought that, I did see the part where the guy was cute on the floor. That was hilarious.
Okay, has anyone gotten as far as number 2? Number 2. This will be a really long quiz, I think.
Oh, it's gonna be like this.
Well, there will be at least a problem like this. Maybe it'll be simpler. Maybe it'll be harder.
Maybe that's the big one. Maybe I think
We do it together.
maybe what again?
Number 2.
Number 2, sure, let's do number 2 together. I'm going to erase number 1.
That was number 1.
I write it down.
Of course, there's also the other, the actual butler.
Okay, so
And
I'm going to give you a little problem-solving advice. That's the best thing I do, is give advice. It's not always good advice, but I'm good at giving it. So it's always good with a problem to draw a picture. Even if there's a picture given, you want to look at it and draw your own version. Okay? So, because maybe their picture isn't good for you. Right, an airplane flies at a heading of 90 degrees. Yeah, you see, they're 90, darn it, they're 90 degrees. They're aviators. In aviation, 90 degrees doesn't mean the same thing it means to us. But we're gonna do it without reference to what north is. All right, airplane flies at a heading of 90 degrees. Well, we're just gonna use, straight all over, right? 90-degree angle. Or, I think I have to, I'm gonna get in trouble no matter what I do. I'm gonna draw it a little lower. Okay, so there it is, it's going 90 degrees, 210 kilometers. That's 90 degrees. It then takes a new course, 160 degrees for 100 kilometers. And then it says, by resolving this latter vector into easterly and southerly components, determine, easterly and southerly, yeah. Well, forget the east and southern. Just resolve it into components. Determine the location of the plane from its starting place. Give its distance and direction. Okay, so what are its components? Well, the first vector is really easy, right? In the x direction, it goes nothing. And in the y direction, it goes 210. This vector is a little trickier. I mean, you could draw it here if you want, right? And what are its components? Well, it's 100 kilometers, and this is now 160 degrees. Well, we want to use trigonometry, and this angle isn't the one we're interested in. It's this angle. So if this is 160, this angle has to be 20. 20? Wait. Did I get that right? What's 180 minus 160? 20. So, all right, now we have a right triangle, we have a hypotenuse, we have an angle. What are these two parts, the two components? Well, sine and cosine, right? Which one is the sine? Opposite. Okay, so 100 kilometers times the sine of 20 degrees. And this one is 100 kilometers times the cosine of 20 degrees. You can just write it this way if I like. But of course you have to think this is in the negative direction. So it's negative 100 cosine of 20 degrees. And this is in the positive direction, 100 sine of 20 degrees. And now it's really easy to add them, right? Just going to add them. And so this is 0 minus 100 cosine of 20 degrees, comma, and I have to squeeze all this in here, 210 plus 100 sine of 20 degrees. All right, well, now I know the vector, now I know this vector here that describes its location. But the problem wants the distance and the direction. So how do I find the distance from this vector? What's the norm or the magnitude of this vector? This is something you better put on your cheat sheet or remember.
The square root of the x and the y.
Yeah, the square root of x squared and y squared. Well, let's x squared 100 cosine of 20 degrees squared plus 210. I'm not doing the calculator for two reasons. One, I don't have one in my hand. The other is, I really think it's a good idea to leave these numbers alone until you're all done. It's best to square it. Okay, that's its magnitude. Now it's just, you know, you could bring in a third grader and have them punch in the numbers, right? Okay, that's the magnitude. What would theta be? Is that a hand? Look like it's this. Go ahead, David.
It's the reciprocal tangent, the arctangent.
I'm sorry?
Is it the arctangent of the exponent?
Arctangent or tangent inverse of what?
100 sine 20 degrees over.
Okay, remember, the tangent is the slope. Remember that algebra? Slope m is y over x. So it's the second part, 210 plus 100 sine of 20 degrees over the other part, 100 cosine of 20 degrees. But now we also want to be careful that when we use our calculator, we're going to get the right value, right? So looking at our diagram here, it's off in this direction.
What's that?
We can translate that.
This doesn't remind me of corporate America. Some people like to take the 2-hour lunch, right?
That's the best part of life.
Okay, so what's going to happen if I ask for the tangent of this guy here? Right? Or another way of asking this is, what is the range of the inverse tangent, the standard range that your calculator produces?
90.
Okay, I'm just going to draw the axes here. This is the range of the inverse tangent, right? It's going to go from however you want, either pi over 2, negative pi over 2 to pi over 2, or negative 90 to 90. So we're going to get actually this number. So what do we want to do to this number, which is negative, to get the actual number? I guess I drew that wrong. No, this is the second quadrant.
I know, the answer.
The answer is going to be in the fourth quadrant. It's going to be the exact opposite. So how do we fix that?
You have 180.
Yeah, 180, yeah. In other words, it's going to give us this vector. We just add 180 to get back to this vector. This is for your calculator. I mean, this statement is true as far as it goes. Just ambiguous as to which value of the inverse tangent. There's an infinite number of them. You got to pick the right one. Well, actually, there's an infinite number of right ones, because you just add 360 to the right one. But if you're going to do it with your calculator, you're going to have to add 180, because this number here is going to show up. I think
I got my answer.
I'm wrong. I'm wrong here. What did I do wrong? Nobody taught me here. Look, minus. That's why. Now everything I said is true. Okay. It's a negative, but if it's negative, the calculator doesn't know whether it's this quadrant or this quadrant, and it will always give you the fourth. If you understand what I just said, you've pretty much mastered trigonometry as far as it goes. Okay. Now again, I have to, for those who came in late, I have to repeat this statement. You'll notice their diagram is different from mine. That's because apparently in aviation, you start, this is 0 degrees going south, apparently. Is that right? And then 90 degrees.
No, the way they do it, the 90 degrees is east.
Yeah, 90, yeah, this is 0. Oh, I'm sorry. I take it back. Yeah, I'm not an aviator, I apologize. North is 0 degrees. And then 90 degrees is that way. So we've actually got the right answer. We give the right angle, but if you want to know whether it's north or south, that's a different question. So bring in flight simulator and reorient yourselves. Okay. I kind of, now I'm going to ask, you know, number 4, forget, unless you're into physics. 3 is kind of a, it's a little like the balloon problem. It's a static force problem. Give it a try. This is a challenging problem. We'll, you know, maybe we'll spend 15 minutes on it, and then we have some stuff I want to wrap up with. It's interesting for those who are still awake. Okay, you want to give that one a try, number 3?
What is,
Oh, wait. The cable.
I'm not sure what it's asking.
Okay. Well, for you and for Yingling, I have to explain. The second sentence says, if the system is in equilibrium.
Okay.
Now, I don't mean to be condescending. You don't know what equilibrium means, right? You do know what it means? No. It means it's not moving. Equal, and I don't know what librium. That's like the drug people take sometimes. Equilibrium. Come to think of it, it's no doubt Latin, and it's no doubt where they got the drug name from. I don't know what librium means.
Let's Google this.
Something to do with movement. Okay, so if the system is in equilibrium, it's not moving, and you have to find the horizontal components acting in the brace to the wall. In the horizontal and vertical components acting on the vertical, I must have a sum vector of 0. Yeah, it's in equilibrium. Okay. I'll help you out with the diagram here. Again, it's always good to draw a diagram. So we have a wall. It doesn't move, right? Walls don't move. And we have a brace here and a brace here. And this is 4 feet. This is 6 feet. And we have 500-pound weight. Oh, I'm sorry. Glasses, 300 pounds. Okay. Find the horizontal and vertical components acting in the brace of the wall. Oh, wait, no. Oh, okay. So what they don't, maybe what it's not clear is, this is a brace. This is just sticking out there, right? This is a cable, right? So we know that the force that we're missing, if we have the 300 pounds, there has to be a total of, or a net of 300 pounds in this direction, right? So that kind of looks like this. Right? But there's nothing there. There's not something holding it up. This is what's holding it up. So this is its y component. But it also has an x component, right? So you have to figure out what the y component and the x component. This thing sticking out is just, you know, whatever the x component is, this thing is pushing out the exact opposite amount, or it would be moving. Yeah, this is the problem with teaching a math class where problems are all physics.
This is a physics class?
Yeah.
It's a math class, but
There's a reason for that.
that it's a math class?
No, there's a reason that there's physics involved, because this is the last class you have to take before you take physics. You can't take physics until you complete this, so they want to really get a base out of this class that's non-relative to physics, which is why you usually use it.
That's fair, yeah.
Math.
Although, if you were like going to go on in physics, you kind of, I guess you could take it simultaneously, but you kind of need calculus to do.
And that's also a very good point, which is why Foothill has physics and like you can make physics that has calculus, or you can make physics that doesn't have calculus. And when you take physics with calculus, they work on stuff like this.
If you want to major in physics, you really need physics with calculus. Right? But there are a lot of other things you need physics for, like if you're pre-med, or you need physics for biology, where you can probably do that. I think any of the UCs, though, they're not going to count as physics class, as a science class, for their entry unless it has.
It counted as a transfer requirement to take their courses, or their physics courses for
Who's courses?
UC, as we were talking earlier.
Yeah.
Just adding to that. Sorry for pretending.
Sorry. Okay. Take a shot at that, and then when we're done, we'll go over it and move on. Yes.
What is supposed to measure?
You're supposed to find the x and y component. There's the y component and the x component of this vector.
That's all. That's
Yeah.
I have kind of a question looking back. It's right
Rise over run, yeah.
What's the state one that I can't whatever assignment
I don't have that good a memory.
But on that equation, that doesn't allow you know this equation and you know
It's too bad to get it.
Just simplify it. Okay, so you're asking a question about the law of cosine.
Probably I solved this differently, or we solved the card differently. Like I figured out that the angle.
Go through the bar, but I wrote it down my street.
I figured out the angle or C, or the vector that was measured.
That's just happening.
Believe it or not, I've seen worse. So, like,
I'm just showing you. I managed to figure it out.
Oh, wow.
Here I know that I'm not big right, and here I can look
Yeah.
I know, this thing goes up under 60, this one is 90, so I added the 2 up, and then subtracted by 350 by the number, and figured out this was, and then I applied the law for the side.
Find this side.
Yeah.
Oh, yeah, that's good. That would work.
Okay, I was wondering.
It's very creative.
Power, which is exactly what this
Yeah.
is. It makes it how much
Actually, the only catch is on this problem. I like that you found it that way,
that's a 1 horsepower.
but it actually tells you to resolve the ladder vector into easterly and southerly components. So they're actually telling you how to do it, which is different from what you did, but I wouldn't force someone to do it a certain way. Have a better way to do it. I looks like a better way to do it.
Yeah, technically speaking, it wouldn't have worked if that line wasn't labeled in a flow. Because then it could be 1 degree off, or
Yeah.
Okay. But since it was, okay, good. This is great. And I never knew you never checked out 4 manga before. 4 or 4 panel.
Oh, right.
From what? Equipment. Oh, I didn't put a cycle. No, dude, don't.
Well, the reason for the phrase these could be different numbers.
It can be. Look, this is not good. Yeah. This is going on. Oh, it's going hard. It's like this is
wall.
Okay, this is what
You should make this as a yeah, make this credit. Yeah,
this one is handmade, but the art style is well.
I remember like this is like 60, 50 on the clock, and then it's so I'm looking at paper, the whole time.
What I've done. It gives me beautiful.
I wish it was that easy. And then this side.
And she has a,
I'll do the problem for that. I don't know why you get the wrong number.
Is it?
Oh, yes,
These are the components.
Let's do it. How about this? We know we're here.
So we know
Mathematics is consistent, and therefore,
That's actually what I did. That's kind of what I'm worried about.
yeah. We found the problem. Maybe fix that.
The rest, because I use that figure to allow someone to use
Yeah.
the degree I got was 21, you got 17 and change, so that's
By the way, in throughout this community about math wants novel law. Yeah. It's so bad. It's really humiliating. Hard to tell which one is.
Well, should we go on?
Yes.
Okay. Sign the cosine. Cosine.
Yeah, like the art style.
Right? Yeah, okay, so we don't.
Now we can find the all the angles. We don't need all of them. So now we can find that. We can find because it'll be x over y, which is x over
I you can see if I entered it correctly.
You definitely never get it from that in the end game. But
68,000. Oh, I got my square root.
Sorry, no.
Has been on next year next year was
That was all the answers.
next year has been
Determine the location for the starting. That's what that's
yeah, that's I think Neptune used that as a deep.
Yeah, that's
this is a vector made of Neptune.
That's the vectoring component. That's not the answer. Assuming the numbers are right. This is not what you're asking.
Spatial variations are asked. I think that was pretty much too easy. But they were making the mistakes that made the reflection of Pippin. You know what Pippin is? Class UMA. All the other characters now Pippin. And every time we get answered, Pippin is Pippin, right? Do you think there are those kinds of fairs? The centers are
if you do with these, you don't find one.
pick up these theories and they use these fairies which are a god and here get one wish ring.
Yeah, we could find this component and this component.
Oh,
yeah.
Pippin's very Pippin as a fairy.
Let's go
And
over. Okay, so we're going to go over this static force problem. Static force, something's not moving. And we're trying to make all the force components add up. This is kind of a physics thing. There's this, they sometimes have this thing they call a normal force. Like if you have 300 pounds sitting on the ground and it's not moving, well, it's obviously being pushed down by gravity, 300-pound vector. Why doesn't it move?
Because it's got to be a vector of the equal.
There's got to be a vector going in the other direction, and that's what they call a normal force in physics. Now, in this problem, we kind of have something like a normal force, which is we've got a bar here, and it's immovable. So no matter how hard we push this way, it pushes back with that force. Okay, so we know that the total vector has to be 0. It's being pulled down 300, so it's got to be being pulled up 300. Okay, so that's the component of this vector in the y direction. Now, to find the component in the x direction, or actually we don't really care what the x direction is, because we know whatever it is, let's just call this force x, then this is going to be force negative x, and they're going to balance. So really what we need to know is what this angle is, and once we know this angle, then we can figure out what this force is. How hard does it have to pull?
The question actually asks for both components to find both of them.
Okay, then we'll find both components. Okay, so does it just want the components? It doesn't want the total?
No, it says horizontal where the cable is. I think in the break. Yeah, the horizontal and vertical components.
Okay, so we already know the vertical component, right? Has to be 300. Here's a. Oh, this is easier than I thought it would be. Well, if you have, I mean, you understand there's kind of like a rectangle here, right? So this length and the length of, think of this as force vectors for a second. This length and this length have to be the same, right? So the ratio of this force vector to this force vector is also the same as the ratio of 6 to 4. That's the tangent of this angle. Does that make sense? I didn't say that very well. Let's find out what this guy is first. Right? So to know what he is, we need to know this angle here, or maybe this angle here. All right, how do we find this angle or this angle?
We use the tangent, inverse.
Yeah, it's the opposite over the adjacent. So it's 4, 6. That's this angle. This is just its complement. Well, it doesn't matter. We can use either angle.
33.7.
Okay, this is 32.7.
33.7.
33.7. So this is going to be 56.3. All right, so now we have an angle, and we know that the, I'm going to call this big F. F is equal to, F times the cosine of 56.3 is going to be equal to 300. I want you to see how I got that. This is the hypotenuse of this right triangle. 300 over f is the cosine, right? Yeah, maybe if I write it that way, it'll make sense. The adjacent over the hypotenuse is the cosine of 56.3 degrees. You have to take a look at this triangle over here, right? So that tells me I can solve for f, and I can find out what f is. And once I know f, then I can find the x component.
Can you finish that one? So f is 540.7.
Let's see.
Someone get some difference?
F is
540.7.
300 over the cosine of 56.3.
Okay, no, I'm 540 pounds. That's how much bearing weight. So we just do components, just like focus pounds by.
So this is 540, 541. There's also a kind of a neat physics principle here. Like this thing is pulling down 300 pounds, and you'd think, well, I shouldn't need more than 300 pounds to hold it up. But actually, if I'm pulling at an angle, you do, right? Because I'm not just pulling against the weight here, but this thing's pushing out this way to keep the wire out. I have to push against that also. Okay, so the force is 541. The x component is 300. How could I find the y component is 300. How can I find the x component? I've got choices here.
There's also the 3 to 2 ratio you mentioned.
Yeah, you could use that. That's the tangent. You use the tangent of this angle. You could use Pythagorean theorem, because it's a right triangle, or you could take this and the sine of this angle. You could do it that way. Okay. Yes, question?
Just tying my hair.
Okay.
No method.
This will be the,
Could you explain to us what exactly will be on the quiz specifically?
Sorry?
What exactly will be on the quiz specifically?
Well, nothing that isn't in, double negative, nothing that isn't in the book.
So what's in the book will be on the quiz?
So what's
So
in
we
the
can
book?
turn to chapter 20 and that's what's going to be on quick.
I didn't understand it.
It's sarcastic.
I thought it was. You need to know. You need to know how to add vectors. You need to know how to draw them. You need to know how to add them by drawing. You need to know how to subtract them. You need to know how to deal with them in the IJ form, the component vector form.
Oh.
Right? You need to know how to do that. You need to know how to compute the magnitude of a vector. You need to know how to find the direction of a vector. And you need to know how to do one of these displacement or static force problems. You don't have to know anything about spinning tops or cross products or any of that stuff.
I just wanted to get that out there.
Yeah. Okay. Are there any other questions like that? Is there something someone wants to see before I take you off into Wonderland? I wonder what he's talking about.
Well, they basically the whole tutorial thing. I think they're late. More than
Now that that guy left, I'm going to tell you the secret of the quiz.
Yes, okay.
I can't. That would be cheating.
Oh, that's fine. You don't mind. You don't mind.
Okay.
You know why that's
I can I can do this pretty quick. I'm really offended by the fact that the book
That's horrible wording.
left out some of the magic. So I'm going to try and, in as clear and as fascinating a way as possible, I'm going to try and introduce you to some of the magic of vectors that the book is missing.
I have a quick thing.
Yeah.
The stuff you wrote on the board, all the properties.
I'm going to talk about it.
Yeah, it's I try to relate what we learned in the past. We learned in the past. I try to relate what we learned in the past and having it relate to the vectors that we're using. Okay.
Yes.
It falls almost similar or same property, or is it?
Yes.
Let me check. It does. Yes.
Yes.
It does. I see.
Okay. So without further ado, somewhere in your past, you should have run into these are properties that you've learned about the real numbers. I don't know, this was always the real weird one. People, have to deal with closure. Not all operations provide closure. For example, square root, right? You can find the square root of numbers until you try it with a negative and then it doesn't work. But adding, every two numbers you add, you get a number. Adding is associative. Everyone know associative?
Yes, look on the board.
Commutative. There's an identity element. You can add it 0 to anything, you get your number back. And we also have this distributive property. And what I want to point out is vectors are not numbers, but lo and behold, they have the same properties. You add any two vectors, you always get a vector. You can add them associatively. Oh, a mistake there. Associative, commutative, you can switch them, doesn't matter. There's an identity element, the 0 vector. And there's actually, when you talk about distributive, you talk about multiplication, because we're talking about scalar multiplication. And there are actually two distributive properties. You can distribute a scalar over two vectors, or you can distribute two scalars over a single vector. So, the little magic I want to bring to you is that it isn't just numbers that obey these properties. And it isn't just vectors either. And there's a very fertile part of math that looks at things that obey these rules without respect to what they are. In other words, if you just say, well, I've got some objects and they do this, what can I say about them? So that's just a very cool thing. You had a question?
Yeah. First thing is more just a basic thing about vectors. Can we basically just think of a vector as a set of two numbers or however many numbers and just treat it like that?
Where you are today, yes, you can. You can think of it as the components of the component vector, or you can think of it as direction and the magnitude, which is completely analogous to x and y coordinates and polar coordinates, right? And you can convert between them, right, using those equations.
But at some point we won't be able to.
Yeah. Now, in mathematics in general, vectors are not limited to that. You could have a three-dimensional vector. You can have a vector which is just an object that has properties that aren't necessarily the same properties that you're used to with numbers. Okay.
Well, there's another thing.
Okay. Like I said, there's a little bit more magic here I want to show you. I want to show you two vector theorems, which you'll find very easy to understand because my explanations will be so clear. The first one is going to be confusing at first. It's called the triangle inequality. And it says that the magnitude of the sum of two vectors is less than or equal to the sum of the magnitudes. Now, it turns out triangle inequality is really, really important in mathematics. But in this particular case, if this is confusing at this moment in time, I'm going to make it really clear why it's true. Right? Let's say this is U, and this is V, and I'm adding them. Well, most of the time I get a triangle. And there's a theorem you should already know from geometry, which is pretty much identical to this. What does it say about the sides of a triangle? Well, the sum of two sides of a triangle is greater than, that's this, the sum of two, is greater than or equal to the third side. That's this. That's pretty, is that pretty simple, pretty straightforward? There are some other cases which are kind of trivial, right? What if U and V are in the same direction? Well, then the sum of U and V is equal to the sum of the magnitudes, yes?
So what exactly does that two line on each side notation mean?
This is, oh, well, I guess you missed that. This is the symbol for the magnitude, right? Or the norm, which is a synonym of a vector.
Mm-hmm.
So what I'm saying is the magnitude of V plus U is always less than the magnitude of V plus the magnitude of U. And again, if you look at this, all you have to do is say the length of this side and the length of this side will always be greater than or equal to the length of this side. Now, again, if they're in the same direction, that's when you get equality. Right? Length of U plus length of V is length of U plus V. And the only other case is, say, U and this is V, and now they're in opposite directions, right? Well, here clearly the length of U plus the length of V has to be greater than what's left, right? So, okay, that's just a really cool thing from vectors. Here's another one. This one's even better. I'll just state the theorem, and then I'll show you why it's true. All right? The theorem says that the norm of U plus V is equal to the norm of U minus V if, are you guys familiar with if and only if? Okay, good. Are you familiar with if and only if?
Yes.
No. Okay, so I want to explain what if and only if means. If I say A if and only if B, that means two things. It means if A, then B. If B, then A. So a theorem usually says if something, then something. But if you say if and only if, it goes both directions. Okay, so these two are equal if and only if U is perpendicular to V. Oh, perpendicular, 90 degrees, right? Okay. You look at that and you go, why? Why would that be true? Okay. Let me cheat and remind you of a theorem that you may have forgotten from geometry. Right? This theorem says that a rectangle is a square is a square if and only if its diagonals are equal. So if I have a rectangle, yeah, if I have a rectangle,
Wait. What?
all right, let's say that right. I think maybe I want a parallelogram.
No, rectangle will.
Rectangle. Okay, so it says if these are equal, then it's a square. And if it's a square, what do I know about the diagonals? They're perpendicular. Right? You know, in geometry, it's a little hazy. This is a theorem you should have learned.
Won't a rectangle always have equal diagonals, though?
I'm sorry. It was a parallelogram.
Well, we've been doing number 4.
Thank you.
So it'd be a parallelogram as a rectangle.
I'm sorry. I got it wrong. I really do. I don't remember my geometry. This is if a parallelogram, it's the same thing except substitute parallelogram and rhombus.
Fantastic. Will we be doing number 4?
That's the ramp.
No, you can practice that, but you won't have anything like that on the quiz.
So the
Yes.
stuff that we went over today will be on the quiz, though? The stuff that we went over in class today will be on the quiz?
There'll be static force problem,
So
and maybe a wind problem, but
there'll be one like number 3, which is one we just said.
I don't have it in front of me anymore.
It's the weight one? The one that's the weight?
The weight indicator.
Yeah, there'll be something like that. Yeah. Yes.
So what does the epsilon mean anyways?
What does the what?
Epsilon in the first example mean, or that E symbol?
Oh, way up at number
Up there?
Yeah.
It's not epsilon, that's the inclusion symbol. It says, if U and B are members, well, here it says, if A and B are members of the real numbers, and A plus B is a member of the real number. And this says U and B are members of something, which I didn't really tell you.
Then B and yours.
It's called the vector space. Okay, all right. I'm gonna try and finish this up real quick. Yeah, if a parallelogram is a rhombus if the diagonals are equal. So all you have to do is think about what U plus V is. And U minus V. Right? So this is U plus V. And this is U minus V. Which is to say, you add two vectors, and it's the sum is a diagonal. You subtract them, you get the other diagonal. And if they're equal, then it's a rhombus, and then the diagonals are perpendicular. All right. I have one more short little thing, and then we can all go. Yeah, make some room here. I showed you at the beginning of the class something which, of course, you're not responsible for, which was how to multiply two vectors in 3 dimensions and get a third vector. But even in 2 dimensions, you can multiply 2 vectors and get something. You can get a number. And this is called the dot product. Right? And the way the dot product works is if you find that what they call the dot product of V and U, it's equal to the magnitude of V times the magnitude of U times the cosine of the angle between them. Now, it turns out, though, that there's another way to calculate the dot product, which is the dot product of V and U is equal to, and now I'm going to use Vx, Vy, Ux, and Uy to represent their components. You know, in other words, V is equal to Vx, Vy. And it's a very simple calculation. Vx, Ux plus Vy, Uy. And since these are equal, these two are equal, which means that there's this neat problem you can solve very simply using this. If I tell you I have 2 vectors, 3, 4, and 6, 9, what is the angle between them? Now that's kind of a hard problem to solve if you don't know about this. But if you know about this, you can just say, okay, what's Vx, Vux, and Vy, Uy? Well, that's 3 times 6 plus 4 times 9. That's 36 plus 36 is 72. And that has to be equal to this. Well, we know everything here except the cosine of theta. Right? 72, all right. V, okay, square root of 3 squared plus 4 squared, that's going to be 3 squared plus 4 squared. 3, 4, blank, right triangle, 5. Times square root of 6 squared plus 9 squared. That's the square root of 36 plus 81. Square root of 36 plus 81 is 117. Cosine of theta. So theta just becomes 72 over 5 square root of 117. Cosine inverse. Okay, it's too bad we don't have that as part of this chapter. It's a really great theorem, great way to do stuff. But that's it. I'm around for any questions. There's points
Isn't it square?
Oh, there it is. Yeah.
Look at that red thing right there. Write it down. My keys. It's easy to cut my keys.
how you're
Lane here? I can't do lane here.
I see people walking around with
You should pull it up and run away. I would do that.
I just run by spam.
I don't know, man. I can bike faster than run.
If you had an ugly time, moment of surprise.
Imagine.
Oh, that's fine. But if people that are in the pocket and now it's as far as an opposite.
I just want to teach a lady to stop biking after. Crash into them with a hand. So guys, Tuesday, have a good special. So guys, quiz Tuesday, we're gonna go get more chill. Y'all after that? I called the limo, you know, just like a little. Didn't think we were going to German branch. Not the library, right? Alright, see you later. Hasta luego. Huevos. Yes. I come from tomorrow. See you later.
Yes, I'll sleep. You don't sleep. Thank you.
The counselor suggests me I can try if I think I'm doing well, I can continue and choose the major instead.
Yeah.
GPA is very important for us, and so.
Well, you know, the math, to be an actuary, is not as hard as math to be a math major. But it's a lot of math.
But I think it's the same because I saw the statistic also to 2B, the math, all math. And
yeah.
That major, I forgot the name, and the economy and math also to 2B. So.
I see. Oh, I see. You have to get to that point. Yeah. Okay. Well, anyway, good luck. And good luck on Tuesday.
Okay. Thank you. Have a good night.
Thank you.